Right, so now we're on question 8, 2016, Maths Leaving Cert Higher Level Paper 2. Okay, so we're looking at the height of the water in a port, which was measured over a period of time. The average height was found to be 1.6 meters. The height measured in meters is h of t, and was modeled using this particular function here. So h of t is equal to 1.6 plus 1.5 cos pi over 6 t. T is the number of hours since the last recorded high tide, and pi over 6t is expressed in radians. So if you're doing this, just make sure your calculator is in radians. Now let's see what we have to do first of all. Okay, so we have to find the period and the range of this particular function here. So let's do that. Well, the period is just simply 2 pi divided by pi over 6. Whatever's in front of the variable here, t, that's what you divide 2 pi by. And that will give us 2 pi times 6 over pi. So that will just give us 12. So the period is 12, and the range then, okay, so your normal cos function will go from -1 to +1. However, the number in front of the cos here is 1.5, so we're going to go from -1.5 to +1.5. However, we're also adding this 1.6. So if we take -1.5, add 1.6, we're going to start actually at 0.1. 0.1. Now, the upper range would have been 1.5, or the upper peak y-coordinate, if you like, would have been at 1.5. We've got to add 1.6 to it, so that will give us 3.1. So this is our range for this particular function here, 0.1 here to 3.1. So find the maximum height of the water in the port. Well, your function is going to have a range of, or a height of 0.1 meters up to 3.1 meters. So the maximum height of the water in the port is going to be 3.1 meters. So that's fairly straightforward anyway, 3.1 meters here. Okay, now let's have a look at the next part then. I've come down quite a bit here. So find the rate at which the height of the water is changing when t is equal to 2, corrected 2 decimal places. Explain your answer in the context of this question. Okay, so we want the rate at which the height of water is changing. So that's going to involve differentiating this particular function here. So we've got to take h of t, which is equal to 1.6 plus 1.5 cos pi over 6 t. So let's differentiate this. We want h prime t here, so that's going to be 0 here. Now, we're going to have the 1.5 anyway in our answer here. Now, if you differentiate cos, you get minus sine. So we're going to end up with minus sine of pi over 6t. However, as well as that, now we have we have to use the chain rule here, so we've got to differentiate the pi over 6t as well. So if you differentiate pi over 6t, you just, with respect to t, you just simply get pi over 6. So this is what we get when we differentiate the function h of t. Now we have to put in t is equal to 2 into this. So at t is equal to 2, so in other words 2 hours after the last recorded high tide, what do we get? Okay, what would the rate of change be? What would the rate at which the height of water is changing be? So let's do that. So h dash t here is going to be equal to, I'll put the pi over 6 here on this side, minus 1.5 sine pi over 6 times 2. Okay, so you can work this out. It's fairly straightforward. You can work that out on your calculator, and what you end up with is minus 0.68 to 2 decimal places. And this is the rate at which the height of water is changing. So the units here would be meters per hour. So it's 0.68 meters per hour is the rate at which the height of water is changing 2 hours after the previous, after the last recorded high tide. Okay, so that's that bit done. Let's have a look at the next one. Okay, I've done some of this already, so let's just have a look. On a particular day, the high tide occurred at midnight. T is equal to 0, so there you go, T is equal to 0 here. Use the function to complete the table and show the height ht of the water between midnight and the following midnight. So, look, we're going up in 3 hour period. So this is T is 3 hours after the previous recorded high tide. So we're going up 0, 3, 6, 9, 12, 15, 18, 21 and 24 hours later. Okay. Now, when you put these values into h of t, you can do that fairly easily yourselves. Just put 0 in, you get 3.1, put 3 in, you get 1.6, put 6 in, you get 0.1, and so on and so on. Now, what we're required to do then is just graph each of these pairs here. So when you do that, you get this here. Now it's a little bit shaky. I'm doing it on a pad here, so it's a little bit shaky. You should be able to do it a little bit neater, but this is what you end up with here. So we have midnight here, 3 a.m., 6 a.m., 9 a.m., midday, 3 p.m., 6 p.m., 9 p.m. and midnight. So you get this periodic function here. Now let's have a look at what we're required to do with this. So the next question is, find from your sketch the difference in water height between low tide and high tide. The difference in height. Well, this is the height along here, along the y-axis. So this is high tide at 3.1 meters. At low tide it's going to be 0.1 meters. So from your sketch, really what you're required to do here, I guess, is just go across here at low tide, read that off there, that's 0.1 meters. Come up here then, your high tide is going to be here at 3.1. So that's going to be 3.1 meters here. So the difference then is going to be just simply 3.1 meters minus 0.1 meters. That gives you 3 meters. That's the difference in water height between low tide and high tide. Okay, so the next one then asks us to look at a fully loaded barge entering the port. It unloads its cargo and departs sometime later. The fully loaded barge requires a minimum level of 2 meters. Okay, so we need 2 meters, minimum 2 meters water level. When the barge is unloaded, it only requires 1.5 meters. So this is loaded, and this is unloaded. So it needs a minimum height of 1.5 when it's unloaded. Now use your graph to estimate the maximum amount of time that the barge can spend in the port given these two parameters here, without resting on the seabed. So when it's loaded, it requires 2 meters, and then when it's unloaded, 1.5. So let's go back to our sketch here. So okay, we're going to look at 2 meters. So it needs 2 meters when it's loaded, and it is 1.5 when it's unloaded. So let's have a look. I'll use a different color here. Okay, so we'll use blue. So 2 meters is here, so if we just go across here, we could use this point here, go down, but if we look at 1.5 here, 1.5 is, let's see, 1, 2, 3, 4, 5 here. If we go across, that's a very short length of time here. Now if we go across, on the other hand, to this part here, you can see here the tide is actually dropping here. So they would have to unload very quickly here in order to keep up with the lowering tide. But if we go across to here, the tide is actually rising. so that will give them a lot more time. So let's go across here to the next point here where it's 1.5, and let's drop it down. So we're going to go down along here. So that's just after 9 a.m. and here we're looking at 3 p.m. So we're looking at 9 a.m. to 3 p.m. or just after 9 a.m. To 3 p.m. So it's 1, 2, 3 hours. So that's about half 9, 9:30 to 3 p.m. Now if the graph was drawn a little bit more accurately, maybe it would be 9, I'm not too sure exactly, but we're really just looking here at let's say 9:30 a.m. and we're going up to 3 p.m. So that's going to be, let's see, 9:30, 10, 11, 12, 1, 2, that's 5 hours 30 minutes. You can see here if you dropped it down here and here, you're only talking about maybe half an hour or an hour at the most, the difference between here and here. The tide is dropping anyway, so it's very difficult to unload at the same rate that the water is dropping, or you know, it's not really going to work here. Really, you need the tide to be rising to give yourself plenty of time. Okay, so that's really it for question 8. That was question 8, wasn't it? Yep, that's it for question 8.